Good morning. We're going to go over the steps for sizing domestic cold water piping. Appreciate y'all making it here. There are 4 steps. It's a real simple process. It involves a flow test, calculate the GPMs, calculate the pressure available to size the piping, and then select the pipe size. If you look on the table on the board, there's 4 tables that we have in front of us, and I want it to kind of go over. This is the water flow test report. This is generally given to us by the person that performs the flow test. This is the calculator for the GPMs. It's an Excel program that, if you look real close, it has all the various types of plumbing fixtures, and all we have to do, simple process, is just include the quantities, and then it does the calculation for you. There's more than just water GPM in here. It also takes care of the sanitary sewer, which will be a later video. But this table is an itemized table that shows where we're starting on the flow test. It shows our GPM, and then it allows us to see what pressure drops and allocations we're providing for, so that we can come out with a leftover PSI. And then this is our sizing table that's in the International Plumbing Code. And we'll go over this a little bit more detail once we get back to it. So let's start back over here at the top. I'm showing a simple arrangement of a flow test where it involves 2 fire hydrants, hydrant 1 and hydrant 2. And you want this flow test to take place as close to the site as possible, so that you're getting a true reading of what's available at that site. Hydrant 1 will have a gauge on it, and what they do is open the valve so that the gauge sees the static pressure where there's no flow. And then hydrant 2 is what's called the flow hydrant. So if you've got this one closed and you have a gauge here and you're reading 60 psi for static, then they say, go ahead and open the 2.5 inch, open the valve, and they're going to flow out a 2.5 inch orifice that's on the fire hydrant. And the 2.5 inch orifice is key to getting the flow pressure. But what happens is, once you start flowing, obviously the pressure is going to drop in the city at this location, and it's going to give us a residual, basically a leftover PSI. And so if these numbers are close, that means you've got a pretty good system. If you see a big drop here, then there's going to be a tendency of having a lot more pressure drop in the system than we would like to see. And then the pitot tube is a separate item that they actually stab in or hold into the flow of hydrant number 2 to get a pitot reading, and then it calculates into GPM. So these 3 items are key, and we must have those in order to get this flow curve. So we've established what the city has available, and then we're going to move to actual project information where we're inputting. We determine where the water is going to come into the building, and it's generally where the riser is. And then we're going to input every plumbing fixture that we have on the project. If you look down here at kitchen equipment, we actually put in 20 GPM on this one. We generally don't get a kitchen plan until after 50%, maybe 75%. It's down the road. So we go ahead and we've done calculations in the past, and it ranges anywhere from 20 to 30 GPM. So it's important for us to make sure that we allow for that. Even though we don't have it, we can go ahead and make some assumptions that are historically sound based on what we've dealt with. So in this case, we're at 95.5 GPM. We got our flow test. We've calculated our GPM. We're at 95.5, so we go back to the flow curve and we plot. I would go ahead and just grab 100 GPM, make it easy on yourself. And then once it intersects the flow curve, you go straight back. You go to the left, and we're going to use 58 PSI to start off with. And so we have 58 PSI here. We went ahead and rounded up our GPM. It's 96. The pressure drops that the water system will see are through the water meter, the backflow preventer, the static head loss, depending on the building height. If the building's 1 story, 2 story, 3 story, then this number here is going to depend on that building height. And simply, basically all you're doing is taking that height from down in the ground to your highest point in the building is multiplying that times 0.43. And that's what the program does for you. So we've got 6 PSI for static head loss. We allow for 25 PSI for the water closet. And this is key because if we don't assume 25 PSI, or we don't allow for 25 PSI to flush the commode, and we leave that 25 in this calculator, then we're going to have a higher number down here, and it's going to force us, or it's going to say, hey, you have more PSI per 100 foot, you could actually get by with a smaller pipe. If you don't allow for the 25 PSI, then you're not going to have this 25 PSI because your lines are going to be too small. They're going to be smaller than they need to be. So running through all these numbers, and you can see we've got 520, so you have to allow for your longest run from where they're tying onto the city main all the way to your furthest, well, I'm gonna say group of fixtures. Maybe it's just a water closet and a lavatory that's on the 2nd floor, and it's, you pick the furthest point from where the water enters the building. And so what we've done is calculate at 520. Now this is already taken into account the factor you use. It's 1.5. And so I want to say it's like 360 feet, and then we multiply it times 1.5, and then that allows for the fittings, the elbows, the T's, the valves, anything that's going to restrict the pipe or the flow in the pipe. And so basically what you're doing is giving it an equivalent footage so that this is longer, and so it's assuming more pressure drop. And so using 13 over 520, that gives us a PSI drop per foot, and then this program multiplies it times 100. So what you're doing is converting it to a PSI drop per 100 feet, so we can use this table. And this table has a lot of lines on it. It can be very confusing if someone doesn't explain it to you. So on this side we've got GPM, this side we have PSI, this is PSI drop. As you go from left to right, your pressure drop per 100 foot goes up. 0 GPM up to, on this table, 9,000. These lines are your velocities. And what we want to do, we want to stay between 5 and 8 feet per second on our velocities. We want to stay 5 feet or above so that the pipe system stays clean. And we want to stay 8 and below so that we're not affecting the inner wall of the piping, because water can be, it can be hard on the material of the pipe if you're flowing too fast. So this is our sweet spot. We want to stay right here. And we're saying that we've got 2.5 PSI per 100 foot, and we're 95.5 GPM. So 95.5 GPM, you come right up here. It's almost 100, obviously. And you come across this line, and then you find 2.5 PSI per 100 foot drop. And you slide your finger up, and where these two lines intersect is a 2.5 inch water line. So that's the size of the line that we want coming into the building. And remember, as you drop GPM, you come into the building with a 2.5 inch serving 95.5, 96 GPM. You want to use the 2.5 all the way through as the line size, as the GPM drops in the building, you use the same 2.5 PSI per 100 foot. So we also have laminated sheets that show groups of fixtures. Depending on the count, it gives us a line size. So fortunately, this is a pretty good flow test for a single story building. They don't always come out that well, So you'll see times where you got good static, but the residual is much lower. And we can add additional videos for those scenarios as well, where we have to do a booster pump, talk about pump suction and how we calculate the pressure downstream. Well, that's about all I have for today, and I appreciate y'all's attention. Thank you.